I want to talk about one of the models that is really the foundation of much of modern growth theory. It's called the Solow model. It goes back to Robert Solow in the 1950s. And in the model, we're going to have households, they're going to save, and they're going to invest those savings in capital, and firms are going to transform that capital into output. But we're going to see that that by itself is not enough to generate persistent growth in output. In fact, we're going to need growth in an exogenous parameter, which I'm going to call total factor productivity, in order to generate persistent growth in the economy. But let's lay out the bits of the model. So I'm going to start with a capital accumulation equation. The change in capital at a point in time is going to be equal to investment less depreciation. Very simple. Investment is going to be equal to savings in this model. It's a closed economy, so investment is equal to savings. And savings are just going to be a constant fraction of output. Output is going to be given by a production function, which is going to look like this. It's a Cobb-Douglas production function, combining capital and labor. We've seen how capital evolves. Now the other two variables here, A and T. A is total factor productivity, and that's going to grow at a constant rate, G. And labor supply is going to grow at a constant rate, N. So these 5 equations make up the entirety of the Solow model, but we can make it even simpler than that. We can boil it all down into one equation. So we can take these, and let's go back to the capital accumulation equation. I'm going to plug in investment, and then I'm going to plug in output from the production function. Now, this equation is not completely describing the model because K is going to accumulate over time. We're going to save a fraction of output. We're going to invest it. And if investment is greater than depreciation, then capital is going to accumulate. But these A and L are a little bit of a problem here. We need to detrend with respect to these variables because these variables are also growing. And the detrending we're going to do is we're going to make a variable called KT tilde, which is capital per effective unit of labor. So it's the capital stock divided by labor supply, but also divided by total factor productivity. And AL is, if you like, effective units of labor supply. So KT tilde is our effective capital stock per worker. Now, KT tilde using the product rule or the quotient rule is going to be as follows. So I've just used the product rule here to give me an expression for KT tilde dot, so the change in KT tilde over time. And I can simplify this, of course. So this is just KT tilde. This is just KT tilde. This is G. This is N. And this we can multiply and divide by big K dot, and we get K dot over K times KT over LT, and that's of course equal to KT tilde as well. So rewriting that, we get KT tilde dot, change in capital per units of effective labor supply over time is equal to this. Okay, so let's plug in big KT dot over KT dot. So the growth rate of the total capital stock, which we know from our capital accumulation equation. It's of course equal to the following. So the KT at the end just drops out and we're just going to minus delta, but this of course is also KT tilde to the power of alpha minus 1. Okay, so let's plug all that into our equation for KT tilde. So KT tilde is equal to K dot over K, which is this, S times KT tilde to the power of alpha. We have alpha minus 1 here, but we're multiplying by K here as well. So that's just KT tilde to the alpha. And then we're going to subtract the delta, the G, and the N times KT tilde. And this is our one equation that totally describes the Solow model. We can draw this equation graphically. So this is KT tilde here, and this is KT tilde dot. And this first part of the equation, we're going to see it's going to be increasing at first, but then eventually KT tilde to the power of alpha is going to increase at a slower and slower rate. And this negative term is going to overtake it. And so eventually it's going to do that. Okay, so this is when you start off with 0 capital per effective worker, you also, the change in your capital per effective worker is also 0. So if you plug 0 in here and 0 in here, you get 0. So if you start off with no capital, you never accumulate any capital. If, however, you start off with a positive amount of capital, let's say A0 here, your capital stock is going to be growing over time. And it's going to grow, and so you're going to move to the right here. It's going to grow and grow and grow until you get to this point here, which I'll call K star. I should really call this K tilde 0 and K tilde star. And eventually you get to this point K tilde star where there's no more growth. If you start off above K tilde star, your capital stock is going to decumulate, it's going to decrease, and eventually you'll go back to K tilde star as well. So we know now that just from using our intuition and a bit of graphical intuition, we know that we have a steady state in this economy and it's given by K tilde star. So as long as we start off with some positive level of capital, we're going to eventually accumulate to the point where we get to K tilde star. Let's figure out what K tilde star is. So K tilde star is defined by the point where K tilde dot is equal to 0. So let's plug K tilde dot equal to 0 in this above equation. Rearranging a little bit, we get the following. Should denote these with stars as well. Can rearrange again. And we get that the level of capital per effective worker in the steady state is given by the following expression. It's increasing in the savings rate, which makes sense. If you're saving a greater fraction of your income, eventually you're going to accumulate more capital and you're going to be able to sustain a higher capital stock in the long run. It's also decreasing in the depreciation rate. I think that's also intuitive. If your capital is depreciating faster, then you need to invest more in order to sustain it, or if you don't invest as much for a given level of S, you can sustain a lower level of the capital stock. It's also decreasing in G and N. So remember, these are the growth rates of total factor productivity and population or labor supply, which may seem a little counterintuitive at first. But if you think about it, K tilde is capital per effective worker. So we're detrending by these variables A and L. We're detrending by productivity and labor supply. So this makes sense. If we are increasing the number of people every year, then we're going to be able to sustain a lower level of capital stock per worker or per effective worker. That's it for now. In the next video, I'm going to look at transition dynamics of capital stock.